In this video, we review how to simplify radical expressions and add them and subtract them too. Let's get started. To begin, let's remember that we could write a radical in two different ways. The first way is your typical radical notation. You might have heard it called a root, a square root, and the term radical here refers to finding the roots, right? So when we're talking about radicals, we're talking about the roots. So when we say a radical, we mean this symbol here. It almost looks like a division symbol, but it has this little curve at the beginning. And we notice that the number here, this little n, is called our index, whereas the number or the variable, the term underneath the radical, is called the radicand. What this index is telling us is how many of a kind you need, how many factors of whatever's inside you need in order to remove it from the radical. Now there's a couple of ways to write it, as I mentioned. One is the radical notation, but the other is the rational exponent notation, where you take the base that's underneath that radical and you raise it to a fractional power called a rational exponent. Now that power is determined by the power of the base, so that's our m in this case. That becomes your numerator of the exponent, and then the n is your denominator of the exponent. So let's practice going back and forth if it's been a while for you. So imagine you see the radical square root of 6. So we see that right here, square root of 6. What that means is it's implied, because it's a square root, the index is implied to be a 2. The radicand, what's underneath the radical, is called 6. So what this is saying is, if you're going to remove something from this radical symbol, you need 2 copies of that factor. Well, right now I could think of this as 2 times 3. Those are some factors of 6, right? But they're not the same, so it would not be possible to simplify the radical any further. We have to leave it as a square root of 6. However, if I wanted to rewrite it another way, which will be helpful as you move on in math, you could definitely do so by recognizing that you could raise 6 to a power, which is a fraction. In the numerator of that fraction, you take the power of your base, or of your radicand, which in this case is a 1. And in the denominator of that power, you take your index itself. So here the index was implied to be a 2. So I could say 6 to the 1/2 power, and that means exactly the same thing as the square root of 6. You might be wondering, who would ever do such a thing? You like the radical notation just fine. Why mess with the good thing? I totally understand your feeling. I hate change as well. However, this will allow us later on to use our power rules for exponents when we move on in math. Especially when we hit logarithms later on in the course, you'll notice that this will be a better way to write radicals. Okay, let's go the other direction, shall we? Suppose you have 8 raised to the power of 1/3. How would you go about rewriting that as a radical instead of rational exponents that they have right now? So you'd begin with a radical symbol. Oops, sorry, lost the top there. There he is. So you begin with your radical symbol. Now who goes underneath it? That's just your base, isn't it? So your base is 8, so that's what goes as your radicand underneath the radical symbol. But as far as your power, that's telling you 2 pieces of information, isn't it? The numerator is telling you the power of your radicand, so that would be a 1. But what did the denominator tell you? You can look back at the top and you'll see what we did before, or look at the note at the very beginning. The denominator tells you the index, doesn't it? So instead of a square root of 8 to the 1st power, this is a cube root of 8, because anything to the 1st power is itself. So you could definitely rewrite 8 to the 1/3 power. Instead of using the rational exponent 1/3 for 8, you could write it as the cube root of 8. And what this means, if you wanted to simplify it, we're going to practice this in our next couple examples, is you would look for 3 of a kind for factors to remove from the radical symbol. For example, in this problem, you could simplify it because 8 is 2 times 4, and 4 is again 2 times 2. There are 3 copies of the same thing. So this time, you could rewrite the cube root of 8 as just the number 2. Why is that true? Because 2 times 2 times 2, in fact, gives you 8. So the root, the cube root of 8, is 2, since 2 times 2 times 2, or 2 to the 3rd power, is 8. All right, so we've practiced, or we reviewed a little bit, how to go back and forth between radicals and rational exponents. Let's head over to our next slide and continue building on these skills. The next slide says we can simplify radical expressions. So if we have it in radical notation, we can simplify such radical expressions using the steps in the box on the right. First, we're going to factor into prime numbers. Prime numbers, again, are the numbers in which their only factors are themselves times 1, right? 2, for example, is a prime number because the only factors of 2 are itself 2 and 1. 3 is another prime number. There are many, many, many prime numbers. In fact, people for years, mathematicians, have been trying to find all of the prime numbers that are possible. They're still trying, okay? They've gotten to a certain number, but they haven't stopped. There are many more. All right, so what we're looking for here is prime number factors of our base, our radicands. Once we've done that, the index will tell us how many of a kind we need in order to remove that factor from the radical. Sometimes, as you saw in the last slide, you completely remove the radical if there's nothing left underneath, right? Other times, you'll have a piece that is still left under as the radicand. For each group that does come out, you're going to bring it outside of that radical, and it's going to leave as a group. And then anytime you bring out more than one, you'll multiply those factors together. And the inside ones that are left over also get multiplied, because when they're next to each other in math, that means multiply. So let's take a look at an easy one, like the square root of 360. Now, for those of you who find radical notation difficult, it's probably because your multiplication skills are a little rusty. So if you go back to some other videos that we've talked about, I've embedded some reviews, some different websites you can go to download apps to work on your multiplication skills if that's something you struggle with. Because the last thing you want to do is have a calculator handy and saying what times what gives me 360. We could do this one ourselves, can't we? Let's take a look. 360 is even, so I could divide by 2. Or I could think of 10, because anytime a number ends in 0, 10 is going into it. I'm going to do that one. 10 sounds nice. 10 times what? 36? Okay. Now, 10 is even again. That's actually 5 times 2. And 36 is actually 6 times 6. Now, if you wanted to, you could break down the 6's, couldn't you? Yeah, 2 times 3 and 2 times 3. But notice, if you already see 2 of a kind, since this was an index, a square root, index was 2, if you already see 2 of a kind, that can be removed as a group. That factor gets removed from the radical. So already I could bring out the 6 in front. So 6 is coming in front. Let's see if anything else comes out. Well, now I just have 5 times 2, or 10. Those are not the same, and they're both prime. So we would actually keep 5 times 2, or 10, underneath that radical. So I would say that the square root of 360 means the same thing as 6 copies of the square root of 10. That 6 in front is really saying that's how many copies of this radical I have. And if you have a scientific or a graphing calculator, or even a basic calculator which has a radical button on it, you should be able to type in both root 360 and 6 root 10 and get the exact same thing on your screen, because they are identical in meaning. They're just equivalents. We would say this 6 root 10 is the simplified version because we've completely brought out any of its roots which were possible. And that's what radicals do. They look for roots. Okay, so let's practice with the next example. Feel free to pause the video and try it on your own. Example 1 says, simplify each radical expression. In part A, we have a very simple one for you to try. The square root of 20. Go for it. Okay, let's see how you did. Did you notice again that 20 could be written as lots of different factors? For example, 2 times 10 or 4 times 5. I'm going to do 4 times 5, but you could have done 2 times 10 and get to the same result, okay? 4 is not prime, meaning I have other factors like 2 times 2. 5, on the other hand, is prime. So this becomes, when you take out the grouping here, the 2 that we have in common, did you get 2 out front? Good job if you did. But there is a 5 trapped under the radical still. So 2 copies of the square root of 5 would be my answer. This is called the exact answer when you've simplified your radical. It's still an exact answer. But once you put it into your calculator, whether it's radical 20, enter, or 2 root 5, enter in your calculator, it'll now give you a decimal approximation. That is not the exact answer anymore, but rather an approximate answer which has been rounded. So keep that in mind. When you're doing word problems or application problems, we typically want the rounded answer because it makes more sense to us, especially when you're talking about distances and such. But if we're talking about a math problem, typically it's not a word problem, just a straight math problem, we would be wanting the exact answer. Okay, take a look at the square root of 112. That's a little bit bigger. If you remember divisibility rules from your previous math classes in school, if a number ends in an even number, 2 goes into it. Also, if the sum of the digits, like 1 plus 1 plus 2 here, if that is divisible by 3, then the whole number is divisible by 3. You can look up on Google divisibility rules, and those will pop right up for you if you want little shortcuts. This one, however, is divisible by 2, but it doesn't look like it's divisible by 3. It may be divisible by 2 more than one time, so like by 4, right? Or even by 6. We're not sure yet. Maybe you know some factors of this number that if you've thought about this one already for a few minutes. But let's take a look at just 2 at the very least, because it's even. 2 goes into 112 how many times? That's right, 56 times. Maybe you started with a different number. Maybe you saw that 4 went into it, and that's another way to go about the problem. Now, if you look at 2 going in 56 times, now let's look at 56, because that's even. Well, we know 56 is 7 times 8, so you're welcome to use those factors. Or if you use 2 again, since it's even, you'd get 2 times 28. Is that what we get here, right? So we get 2 times 28. That's another option. Now notice something. We're going to continue with 28 in a moment, but do you see that we already have a pair of the same number, the same factor 2? So already I'm noticing that I could pull out a 2, and I might be pulling other things out. I probably will, because that 28 can be broken down further. So let's continue. 28 is even. You could think of 4 times 7, or you could think of 2 going in. I'll do 4 times 7, because that's pretty cute, right? We like that factorization probably. And 4 is really 2 times 2. The square root of 4 is 2. That's what's coming out from that pair. So we notice again another 2 coming in front. Now what do I do with that? I multiply it by whatever's next to it in front already. So 2 times 2 will be our coefficient of the radical. So we would say now that we have 4 copies of our radical. But what is our radical? Is anything left underneath there? Yes. In fact, 7 had no partner. So 7 would be underneath that radical. It's called the radicand. The final simplified version of the square root of 112 would be 4 copies of the square root of 7. And you can know you're right by putting it in your calculator and seeing that they mean the same thing. Okay. Did you try C? If not, pause the video and see if you could do it on your own. All right, so in C, which factors did you pick? Maybe you said it's even, so 2 goes into 150 75 times. Maybe you said, hey, I think 15 times 10 sounds nice. Or maybe you did different ones, like 3. 3 goes in there how many times, right? I'm going to do 15 times 10. I think that sounds like a fun plan. But you can pick your favorite 2 factors to begin with. We should end in the same spot. Now that I have 15 and 10 on my screen, I'm going to say, okay, 10 is really 2 copies of 5. Those are both prime, so I can't go any further. 15 is really 5 times 3, or 3 times 5. You can put them in either order. I like to put the 5s closer together because, as you can tell, we are looking for pairs for square roots. There's a pair of 5s. So right now I'd have 5 in front and a radical. Well, what's underneath the radical? What's the radicand? Whatever's left. 2 and 3, when you multiply 2 times 3, what do you get? 6. Yep. So if you said my answer is 5 square root 6, that should be correct. And you, again, can verify that, put that into your calculator, and see that it means the same thing as the square root of 150. So simplifying radicals is a skill you'll need to become proficient in this class and any other math class you go into that's algebra based. It's not always going to just be numbers either. We're going to start seeing variables, so get ready for it. All right, let's continue with our notes. Now let's talk about multiplying radicals together. It turns out we can multiply radical expressions together. And the way we would do that is noticing that here in this little box down here, that you can multiply the nth root of A times the nth root of B. So basically, as long as those two indices, the index n, the index n, match, then you can simply combine their radicands, that means whatever's underneath the radical symbol, you can multiply them together and make them a single radical. So you get a product that way. So for example, here I have square root 21 times square root 3. Because they're both square roots, I'm allowed to multiply the radicands, which are underneath the symbol, together. Okay? Now there's a couple ways to go about this. There's a long way and a short way, and I'm going to tell you my preference is the short way. But I want to point out something to you before we go into this example. The only reason that we can multiply this way is because the index for 21 is a square root, is 2. And the index for square root 3 is also 2. They match. If one of them was a cube root, so an index of 3, and one of them was a square root, index of 2, you could not multiply this way. You would need to first switch to rational exponents and use your power rules. So that's going to require a little bit higher level of thinking than we're doing in this problem here. Just wanted to let you know the difference there. So let's take a look here at how this approach works for this type of situation. we could say that we have a single square root where we have 21 times 3 underneath. And that was because they were both square roots. We could put them together this way. All right, notice this only works for multiplication, not for addition or subtraction. A little bit different. All right, so what we could do now, technically, you could say, well, 21 times 3 is 63, and then you could work on simplifying 63 if possible. Totally valid way of doing things. I find most students tend to do that because they feel like they're being told to multiply when they see the dot there, right? And I totally understand why you would do that. But keep in mind what you're going to try to do in a moment. You're going to try to go back down to the roots, right? That's what radicals are asking you to do, go back to your roots. So in order to do that here, why not start out that process right away? Here's what I mean. I know the factors of 21 are 3 times 7. I'll write it this way, 7 and 3. And by recognizing that, what I really have, instead of 21 times 3 under the radical, I have 7 times 3 times the other 3, which I got from multiplying by root 3. Now I see a grouping, don't I? I see 2 of a kind. So that 3 can come in front. I have 3 copies of square root 7. So 3 radical 7 would mean the same thing as the square root of 63, or the square root of 21 times the square root of 3. You could put any of those in your calculator and get the same exact result. So I wanted to point that out to you. That's a lot faster, in my opinion, than doing the square root of 63 and then simplifying it until you get down to 3 root 7. It requires an extra step. So I'm trying to save time, but if you need to, you could have done it that way. Right, you could have said 63 is 9 times 7, and then you'll see how 9 is a pair of 3's, and we get the same answer. Okay? Just saying there's a couple ways to look at that kind of problem. Let's practice this skill in the next slide. Example 2 says, multiply if possible. In part A, we have the square root of 6 times the square root of 8. See if you can pause the video and try this on your own, just like we did the last problem. All right, let's see how you did. So my advice to you was to break them into their roots first, their factors first, their prime factors. 6 times 8 is going to be underneath that radical, but we thought about, okay, how do we get 6 and how do we get 8? 6 is really 2 times 3, or 3 times 2. I noticed ahead of time that 8 has some 2's in it, so I wanted to put the 2's closer together for my convenience. 8 is really 2 times 4, and 4 continues to be 2 times 2. Now that's completely prime, right? We factored all into primes. What do we do next? What did you do next? Did you look for pairs? I hope you did. We had a pair of 2's there and another pair of 2's here. Now some of you might have done instead the square root of 48. You don't have to admit it, you don't have to raise your hand, but you know who you are, right? That's okay. If you did that, you could have noticed that 48 was really 4 copies of 12, or 6 copies of 8, you're back to where you started, right? And 12 is really 4 copies of 3. And that might have been a faster way for you, because now do you notice that you have a 4 and a 4? That means that we should be able to pull out a 4 and be left with the square root of 3, right? So 4 square root of 3 would be our answer that way. Is that what we're going to get here, this way? Well, we had a 2 come out. Okay, let's write it. We had another 2 come out. Okay, let's write it. 2 times 2. And what was trapped underneath? That prime number 3. So we ended up getting 4 copies of the square root of 3. So yes, in fact, it's exactly the same. All right, so you could have approached it various ways depending on if you multiply first or if you break it apart first. Okay, let's see how you do in B. Again, feel free to pause the video and try it on your own. In B, we have square root 3 times square root 27. So you're welcome to multiply them together first. That's radical 3 times 27. And I believe you'd get radical 81, and you could break that down, 9 times 9, and end up getting 4 3's to work with. Similarly, if you just broke down the 27 to begin with into 3 times 9, and 9 is 3 times 3, notice we have 4 copies of 3. So if this was a 4th root of the 81 number, the answer would just be 3. But because it's a square root, we are looking for 2 of a kind. So we have 2 of a kind there, and 2 of a kind there. Kicking out each of them, we get kick out a 3 here, times kick out this 3 here. Is there anything left? Nope. So this is just the number 9. In other words, that's the square root of 81, isn't it? Because 3 times root 27 was 81, and 81 is 9 times 9. So that's definitely the answer. It is 9, but you could have gotten there from a variety of paths. Now, C can be a little bit confusing for students, so let's make sure we understand what it's saying. It has parentheses, and then inside you have the square root of 10, and then outside the parentheses you're raised to the second power. So it's really saying, if you read it in a math sort of way, the square root of 10 squared. Now, when you're in math problems, like the ones we're going to be doing this semester, oftentimes you're going to need to square both sides to lift the radical, and that's what's happening right here. When you multiply a square root, index 2, times itself, which is what this says, right? This is saying square root of 10 times the square root of 10. Because those radicands, the 10s, are the same underneath those radical symbols, that should end up being just 10. And let's see why that is. Because this is really the square root of 100, you could write it that way, or 10 times 10 under that radical. And we know that if you're doing a square root, you need 2 of a kind. We have 2 of a kind, so we'd bring it out front, but there's nothing left underneath. So it is in fact true that when I square the square root of 10, I just get 10. You could also think of it as the square root of 100, which is 10 times 10 underneath, or just 10 for your final answer. Okay, so either way, you get to the same place. So keep in mind, squaring a radical, a square root, lifts the radical. What if this had been a cube root? How many copies would I have needed? 3. You got it. So you'd have to raise both sides to the third power if that was your equation. And we'll deal with that more as the semester progresses. So let's head over to another skill we need to talk about, how to combine radicals together. Not just multiplication, but addition and subtraction. Here we go. We say that 2 radicals are called like radicals. It kind of sounds like terms. Like radicals, if they have exactly the same index and the same, there's a typo here, exactly the same index and the same base. Another word for base is radicand, right? So let's see what I'm talking about here. I have 2 square root 3 and 5 square root 3. Notice that square root 3 and square root 3 look identical, don't they? They're both square roots, means their index is 2 for both of them. And their radicand, the number underneath for the base, is 3 for both of them. This is kind of like if I had 2x and 3x. They have the same base x and the same power 1. We would have called those like terms. So how did we add 2x plus 3x in math? Do you remember? Yeah, we add the coefficients, don't we? But we keep x the same. We keep it by itself, what it was. It stays what it was. That's saying I have 2 copies of x plus 3 copies of x. I end up with 5 copies of x. Similarly, we would just add our coefficients here, wouldn't we? 2 copies of root 3 plus 5 copies of root 3, in our case, would be 7 copies of root 3 when I combine them by addition. So if I asked you to add them together, you get 7 copies of root 3. Okay, so the only time I can add radicals together is if they have the same radicand and the same index. So if possible, if needed, you'll simplify your radical first, and then you'll have the same radicand, the same index, and combine your like radicals this way. Let's head over to our page of examples and see if this is making any sense. There will be some letters there, so deep breath. Let's not give up. Take a look at example 3 with me. It says multiply if possible. Ooh, another typo today. Your professor must have been sleepy when she wrote these. This should actually say add or subtract. So if you're trying to have proper notes, you can change those. And by the time you get this video, I'll probably have already changed this. Okay, so add or subtract for me. So here's what we need to do to add or subtract radicals. We need to have the same radicand and we need to have the same index. So in order to do this, we sometimes will have to simplify first. In A, you should be able to do this exactly the way it looks right now. So pause the video and see if you can get the right answer. A says 8 square root 14 minus 5 square root 14. See if you can get the right answer. Go for it. Okay, let's see how you did. Notice we had exactly the same radicand and exactly the same index. So we had square roots and they're both of 14, right? So how did we combine these by subtraction here? That's right, because they're like radicals, we simply combine the coefficients, but we leave the radical the way it was. 8 minus 5 is really 3. So did you get 3 copies of the square root of 14? Good job. Now the only thing you'd want to check before you call it a day, right? You want to simplify if possible. 14 is not prime, right? We can think of factors of 14, like 2 times 7, But those now are prime, and they're not the same. So since they're not two of a kind, you can't lift them from the radical. You can't remove them from the radical. So this would be as simplified as possible. Okay, now in B and C, this is where you might get a little nervous because now you see some variables, some unknowns. But we're still going to approach them the same way. I'll do B with you, and then try C on your own. Okay, so in B, we ask ourselves again, root 27x, what are the factors possible there? Well, we would definitely have 3 times 9 times x, right? 3 times 9 times x. And 9 is really 3 times 3. So do I have 2 of a kind? To remove from a square root, we need 2 of a kind. Yes, I have a pair of 3's, don't I? So I could rewrite the first radical as 3 in front of the radical. That's our coefficient of the radical. But notice that the other 3 and the x are still trapped under the radical. Those are called our radicand put together. So underneath the radical symbol, we would still have 3 times x, or 3x. So did you have 3 copies of 3x under the square root? So 3 square root 3x. Okay, great. Let's see if the second radical simplifies at all. 12 is really 2 times 6, or 4 times 3. I'll do 4 times 3, so, or 3 times 4, whichever you like better. And then we still have an x there. Now we'll talk about x in a moment and how it could have been different in the problem. But let's continue with what we have. 4 is a pair of 2's, that's right. So what do we need to remove something from a square root? 2 of a kind. I have a pair of 2's here, so I could pull out that 2 in front. Now who would be left under that radical? Just the 3, that's prime, and the x. 3 times x is also known as 3x. So I have 2 copies of the square root of 3x from simplifying the square root of 12x. But notice what I was asked to do. The directions were actually supposed to be to subtract these 2 radicals. Can I do that now that I've simplified each radical? Well, yes, because the index for each of them is the same. It's 2, because they're both square roots. And the radicand for each of them is 3x. So yes, it's comparing apples with apples, right? If I have 3 apples minus 2 apples, how many apples do I have? Just the 1. So this should have been 1 copy of the square root of 3x. But to say 1 copy of something is irrelevant when you have the something. You can just list the something. It's just the square root of 3x. They're both the same, so if you'd like to write the 1, feel free. You won't be judged for it. All right, try C on your own, and then come back and see how you did. All right, so in C here, we had the square root of 18x plus the square root of 50x. Did you break apart 18 into its factors? For example, you could have 2 times 9 or 3 times 6. I would probably do the 2 times 9 because I know 9 is a perfect square, but you're welcome to have done it 3 times 6. That's also fine. So if I did 2 times 9, which is what I said I'd do, 2 times 9 for 18, and then we still have this x, right? 9 is a pair of 3's, and let's see what that brings us to. A pair of 3's comes out. Did you do that? Awesome. So you have 3 in front, and underneath that radical, what did you write? 2 times x. Good job. You got 2x, didn't you? Hopefully. If not, go ahead and write down where you made your error, because as humans, we usually make the same mistake over and over again, so you want to start reprogramming your brain to find that error before you make it. All right, let's take a look at root 50x. That was really 5 times 10, or you could have done 2 times 25. I probably would have done 2 times 25 for that same reason as last time, since 25 is a perfect square. So if I did 2 copies of 25, and then the x is still there, 25 is a pair of 5's, which will allow me to bring out a 5, won't it? So I'd really have 5 in front, and what did you put for your radical again? That's right, the 2 and the x multiplied together, 2x under the square root. Now we're asked to add these radicals if possible. That was the symbol here in the middle. Add the 2 radicals if possible. Once you've found like radicals, how did you do this? Yep, you just added the leading coefficient. So 3 plus 5, 3 copies of something, plus 5 copies of the same thing, apples and apples. That's really 8 copies of that item. 8 copies of the square root of 2x. So these skills can seem very tedious and lacking real-life application, but I promise when we get into our word problems later through the course, you're going to need these skills. So we're going to need to be really, really comfortable simplifying radicals and combining them correctly. All right, So let's see what we have left. Well, that concludes our slides for this video. So what you want to do is practice yourself. Can you break apart a radical into its components? Can you add and subtract radicals yourself? Can you square and multiply radicals together? If so, you're going to be ready for the next video. All right? Practice, because math is not a spectator sport, and I'll see you next time.